Hello students. So today we are going to discuss electromagnetic induction NCERT section 6.7 and example 6.8. So this is the disclaimer. Learning objectives. After this lecture you should be able to understand the concept of inductance, flux leakage, linkage and mutual inductance. Derive the mutual inductance for two coaxial solenoids. So the index of topic that we are going to discuss today is index, which is indexes NCERT section 6.7 inductance, NCERT section 6.7.1 mutual inductance, and example 6.8. So let's begin with NCERT section 6.7 inductance. So what is induction? So we are discussing about electromagnetic induction. So basically what is induction? So electric current can be induced. So induction means to induce something. Okay, we are inducing the EMF. Okay, so electric current can be induced in a coil by changing magnetic flux from another nearby coil or by changing its own magnetic flux. Okay, so electric current can be induced in two ways. Okay, the two ways that is we are going to discuss. One way we are going to discuss in today's lecture and one way we are going to discuss in tomorrow's lecture. Okay, so what are the two ways? First way is by changing magnetic flux from another nearby coil or by changing its own magnetic flux. Okay, so there are in first case there are two coils. Okay, so changing magnetic flux of other coil with the help of another nearby coil. Okay, or we can say inducing current in the other coil with the help of changing magnetic flux in the nearby coil. Okay, so and the second case is by changing its own flux. Only one coil is there. We are going to change the current or magnetic flux or magnetic field of the same coil, and EMF will be induced in the same coil also. Okay, so electromagnetic induction happens between two separate coils. Okay, mutual. When there are two separate coils are there, then the induction is called mutual induction. Okay, when only one coil is there, we are inducing EMF in the same coil by changing its own magnetic flux is known as self induction. Okay, and inducing EMF in one coil by changing magnetic flux in the another coil nearby, which is placed nearby, is called mutual induction. So what is mutual induction? Occurs when flux change in one coil induces current in the nearby coil. Okay, there are two coils. Flux, we are changing magnetic flux in the one coil and current will induce in the nearby coil. Involves two separate coils. Examples are transformers. Okay, we are going to discuss transformers in the next chapter, alternating currents. Okay, you will see that there are also two coils. Okay, in the transformers also, and we are going to use we will be going to use the concept of mutual induction in transformers also. Okay, and wireless chargers. Okay, nowadays there are wireless charges. Okay, so that wireless charging is done by mutual induction. Depends on relative position and orientation of the coils. Okay, mutual induction and amount of EMF induced in the nearby coil depends on the relative position of two coils and their orientations, how they are placed with respect to each other. Second one is self-induction. So occurs when flux change in a coil induces current in itself. Okay, we are changing the magnetic flux in a coil and current or EMF is inducing in the same coil. That is called self-induction. Involves single coil. Okay, so it involves single coil. There are no two coils, one coil is there. We are changing magnetic flux in one coil and current is inducing in same coil. Examples are inductors. Okay, in next chapter we are going to discuss in detail the inductors. What are inductors? Okay, and we are going to discuss the circuits in which inductors are used. Okay, and one is choke coil. Depends on coil's physical properties, that is turns and core material. Okay, so self induction depends on the core material that is placed inside the coil. Okay, so the relative permeability of this material and also the number of turns of this coil. So important relations to recall before derivations of inductance. So magnetic flux phi b through a coil is proportional to the current I. Okay, so the magnetic flux that is linked with the coil is proportional to the current I flowing through it, or we can say magnetic flux change of magnetic flux through a coil is proportional to current flowing through it. Okay, so it is directly proportional to current flowing. Okay, general relation between phi I and B is, we know that change in magnetic flux is also proportional to the magnetic field. Okay, what is the formula for flux? That is Ba cos theta. So flux is also depends upon magnetic field also. Okay, so magnetic flux also proportional to magnetic field, and magnetic field through a coil is proportional to current. Okay, in solenoid we have discussed what is the magnetic field inside the solenoid, that is mu naught Ni. So magnetic field is proportional to current and magnetic flux is proportional to magnetic field. So there is a relation between magnetic flux and current also. So magnetic flux, change in magnetic flux, or we can say magnetic flux through a coil is proportional to the current flowing through it. Okay, so magnetic flux directly proportional to magnetic field and magnetic field directly proportional to current. Okay, so rate of change of magnetic flux with respect to time is, so the above relation, that is phi b directly proportional to I, we are going to differentiate it with respect to time. Okay, so rate of change of magnetic flux, so d phi b upon dt, rate of change of magnetic flux d phi b upon dt is directly proportional to di by dt. We are going to differentiate on both sides. Okay, so change in magnetic flux will be proportional to change in current, change of current in the coil with respect to time. Got it? From this expression we have derived this. So we know that magnetic flux is proportional to, magnetic flux through a coil is proportional to current. How? Because magnetic flux proportional to magnetic field proportional to current. That's why magnetic flux is proportional to current. And we are going to differentiate it. That is rate of change of magnetic flux with respect to time, that is d phi b upon dt is proportional to di upon dt, means rate of change of magnetic flux is directly proportional to rate of change of current in the coil. Okay, so what is flux linkage? So there is a coil, one coil, there is a coil having number of turns 1, n equal to 1 turn. Okay, so magnetic field direction is shown by the violet lines. Okay, so what is the flux through that coil is Ba, because magnetic field lines are perpendicular to the plane of this coil and parallel to the area vector. So Ba cos theta, Ba cos 0 degree, cos 0 degree is 1. So magnetic flux through this coil having one turn is Ba. If this coil is consisting of n turns, 1, 2, 3 or n number of turns, okay, then flux linked with this coil will be, flux linkage of the coil is will be n into phi. That phi is the flux linked with one turn. Okay, and flux linkage of a coil is n into phi, means flux linked with the n number of turns, that is nba. Okay, so if a closely wound coil has n number of turns and magnetic flux phi b is passing through it, then each turn experiences the same magnetic flux phi b. Okay, so this coil is closely wound, means it is tightly wound, its turns are very close to each other. Okay, so if a closely wound coil having n number of turns and magnetic flux phi b is passing through it, then each turn experiences the same magnetic flux. Total magnetic flux through the closely wound coil is n phi b and is known as flux linkage. Okay, so the magnetic flux that is linked with all the turns of the coil is known as flux linkage. Okay, so flux linkage in this case will be n into phi b. Phi b is the magnetic flux through one turn. Okay, definition of inductance. For a closely wound coil, flux linkage is proportional to the current I flowing in the same coil or nearby coil. Okay, so flowing in the same coil is the case of self induction. Okay, and the nearby coil is the case of mutual induction. Okay, so for a closely wound coil, flux linkage is proportional to current I. Okay, means n phi b is directly proportional to I. So it is applicable for both mutual induction and self induction. Okay, so flux linkage is directly proportional to current flowing through it. So n phi b will be equal to Li, and this L is the constant of proportionality, which is known as inductance also. Okay, L is constant of proportionality and known as inductance, which relates flux linkage with the current. Okay, L is a scalar quantity, inductance is a scalar quantity, and its SI unit is Henry, and it is represented by H, capital H. Okay, got it? Magnetic flux directly proportional to I, and n phi b, magnetic flux linked with n number of turns, that is flux linkage. It is also proportional to I, and after removing sign of proportionality, we got a constant, that is constant of proportionality, also known as inductance. Okay, and it is scalar quantity and unit is Henry. So inductance is of two types: mutual inductance and self inductance. Let us derive the expression of 6.7.1 mutual inductance for a coaxially placed solenoids. So mutual induction, what is mutual induction? We have discussed already. So phenomenon where an EMF is induced in a coil due to change of current in another coil. Okay, there are two coils and current is flowing through one coil, any one coil. Okay, so current is flowing through the coil due to which magnetic field is produced, and there is a magnetic flux through that coil. Okay, so change of the current, if we are changing the current, magnetic field will change, magnetic flux through the coil will also change. Okay, so phenomenon where an EMF is induced in a coil due to change of current in the another coil. We are changing the current in the another coil and EMF is induced in the another coil. Okay, so this is due to the change in the magnetic field. Due to the change of current, magnetic field is changing, also magnetic flux through the coils is changing also. Okay, so this phenomenon is called mutual induction. So you can see this diagram, there are two coils. Okay, one coil is this coil 1, this coil is coil 2. Okay, current is flowing through that coil. This coil is connected to a AC power supply. Okay, because AC power supply, AC source, current is not constant. Okay, current it is having different magnitude at different time. Also polarity of the current is also being changed. Okay, we can use the DC source also, in which we can change the amount of current in the circuit also. Okay, so they have taken AC power supply. Okay, so current is flowing through this coil, due to which magnetic field is there, and due to this magnetic field there is some flux, there is some magnetic field lines that are passing through that coil 2 also. So there is magnetic flux through that coil 2 also. we are changing this current, so this magnetic field is also changing. So magnetic flux through this coil 2 will also change, and due to change of magnetic flux through this coil 2, there will be, we know that EMF is induced due to change of magnetic flux through coil. Okay, so if magnetic flux is being changed, so there will be EMF will be induced or current will be induced. So induce current. So this is the direction of induced current. It is shown in the diagram. So mutual inductance. It is the property of two coils placed nearby that describes how a change in current in one coil induces EMF in another coil. Okay, so if we are changing current in the one coil, then current will induce in the second coil. This is mutual inductance. It is property of two coils. So it is a scalar quantity. So mutual induction is phenomenon. Mutual inductance is property. Okay, so it is a scalar quantity, and the SI unit of mutual inductance is also Henry, H. Derivation of mutual inductance for two coaxial solenoids. Okay, now this is the figure. So there are two coils. One is S1. Inner coil is S1. Outer coil is S2. Current is flowing through any. We can assume current in any one of the coil, in inner coil or in outer coil also. Okay, we are going to discuss both cases, when current is flowing through S1 and when current is flowing through S2. We are going to discuss both the cases. Okay, so radius of inner coil is R1, radius of outer coil is R2, length of both the coils is L. Okay, so there are N2 number of turns in the outer coil and N1 turns in the S1 coil. Okay, figure 6.12, two long coaxial solenoids of same length L. So consider two long coaxial solenoids of same length L. Inner solenoid S1 with radius R1 and number of turns per unit length N1. Okay, so there are capital N1 turns in the S1 coil, and number of turns per unit length will be, that is capital N1 upon L will be small n1, that is number of turns per unit length. So inner solenoid S1 with radius R1 and number of turns per unit length small n1. Outer solenoid S2 with radius R2 and number of turns per unit length N2. Total number of turns in S1. So total number of turns in S1 will be number of turns per unit length into length. So capital N1 will be equal to small n1 into L. Number of turns, total number of turns in S2 will be, capital N2 will be equal to small n2 into L. So case 1, we are going to discuss two cases. So case 1 is when current I2 flows through S2. Case 2 that we are going to discuss will be when current I1 flows through S1. Okay, so we are going to discuss both the cases when current is flowing through any one of the coil. So case 1, when current I2 flows through S2, it produces flux phi1 through S1. Okay, you can see the diagram. So current is flowing through S2, that is I2. Okay, so it produces flux phi1 through S1. So due to the current flowing through S2, so what is the mechanism here? Due to the current flowing through S2, magnetic field will produce magnetic field inside the solenoid. Okay, S2, current is flowing through S2. So magnetic field will be produced inside S2, and this S1 is also placed inside the S2 coil. Okay, so due to the magnetic field of S2, there will be some magnetic flux through this S1 also. Okay, so that magnetic flux is known as phi1, which is through S1. So flux linkage with S1 is proportional to current I2. Okay, so why flux link with S1 is proportional to I2? Because the flux through S1 is due to the current flowing through the S2 coil. Okay, current is only flowing through the S2 coil. Okay, so flux linked with this S1 coil will be due to current flowing through S2 coil. Okay, so N1 phi 1, that is the flux linkage with the S1 coil. Number of turns into flux linked with one coil, one turn. So N1 phi 1 will be proportional to I2, current flowing through S2. So N1 phi 1 will be equal to M12 I2. So after removing this proportionality sign, there will be some constant. In case of generalized, in generalized expression, the constant was L. That was inductance. But in case of mutual induction, the constant of proportionality will be mutual inductance. Okay. So that M12 is mutual inductance. So mark it as 6.7 equation. So where M12 is the proportionality constant known as mutual inductance of solenoid S1 with respect to S2. Okay, so this 1 2 means mutual inductance of solenoid 1 with respect to solenoid S2, or coefficient of mutual induction. So mutual inductance is also known as coefficient of mutual induction. Okay, case 1 is going on. Now, magnetic field inside S2 due to current I2. So due to current I2 flowing through this S2, magnetic field inside S2 will be B2. So B2 will be mu naught N2 I2. That is the magnetic field inside this S2, because current is flowing through this S2. So we know that magnetic field inside the solenoid will be B equal to mu naught Ni. So B2 will be equal to mu naught N2 I2. So flux linked with the solenoid S1. So S1 is not carrying any current for now. Okay, only S2 is carrying current I2. So magnetic field that is inside the solenoid S2 is also inside the S1. Okay, so flux linkage with the solenoid S1 will be B2, that is magnetic field produced by S2, into area of cross section of S1. Okay, so you can visualize this, that magnetic field lines are passing through this S1 coil. Okay, so area of this S1 will be considered, but magnetic field of this S2 will be considered. Okay, so flux linkage with solenoid S1 will be N1 phi 1 will be equal to N1. What is phi 1? Flux linked with S1 coil, that is magnetic field produced by S2 coil B2 into area of this S1 coil A1. Okay, so after putting the value of A1, what is A1? Area of cross section of this S1 solenoid, that is pi R1 square. Okay, what is B2? B2 is mu naught N2 I2. Okay, so N1 phi 1 will be equal to, what is capital N1? We have discussed that capital N1 will be equal to small n1. Small n1 is number of turns per unit length of first solenoid into length of the solenoid. Okay, so N1, capital N1 will be N small n1 L pi R1 square mu naught N2 I2. Now club all the things. So N1 phi 1 will be equal to mu naught N1 N2 pi R1 square L I2. Okay, after clubbing all the values, you will get this. Mark it as 6.8 equation. Okay, substituting N1 phi 1 equal to M2 M12 I2. Okay, that thing we have seen in the previous slides, that N1 phi 1 flux linked with this S1 coil, flux linkage of this S1 coil will be proportional to current flowing through this S2 coil. And after removing proportionality sign M12, this proportionality sign appeared. Okay, so substituting N1 phi 1 equal to M12 I2 from equation 6.7. Now comparing these two equations, N1 phi 1 equal to M12 I2 and this 6.8 equation. So you will get M12 I2 will be equal to mu naught N1 N2 pi R1 square L I2. Okay, so I2 is common here. Only now M12 will be mu naught n1 n2 pi r1 square L. So m12 will be equal to this, mu naught n1 n2 pi r1 square L. Okay, so mark it as 6.9 equation. This is the mutual inductance of S1 coil with respect to S2 coil. Now case 2. So what is case 2 now? Current I1 flows through the solenoid S1. Okay, now no current is flowing. Now case 2 is no current is flowing through the S2 coil. Now current is flowing through the inner coil S1. So when current I1 flows through solenoid S1, it generates a magnetic flux phi 2 through S2. Now in case 1, due to the current flowing through S2, there was a magnetic field inside this solenoid, and that magnetic field was inside this S1 coil also. Okay, so we calculated the flux linked with this S1 coil. Now we are going to calculate the flux linked with this S2 coil due to the current flowing through this S1 coil. Okay, so magnetic flux linkage with S2 coil will be N2 phi 2 will be equal to M21 I1. Okay, in case 1 we have seen that N1 phi 1 equal to M12 I2. Now in second case, N2 phi 2 will be equal to M21 I2. Mark it as 6.10 equation. So this M21 is the mutual inductance of second coil with respect to first coil. This is constant of proportionality again. So M21 is the mutual inductance of solenoid S2 with respect to solenoid S1. So magnetic field inside S1 due to current I1 is. So now current is flowing through this S1. So magnetic field inside this solenoid will be B1 equal to mu naught N1 I1. So N1 is the number of turns per unit length of this S1 solenoid into I1, current flowing through this S1 solenoid. Okay. Now flux linked with the solenoid S2. Now here you can focus what is the change. So N2 phi 2 flux linked with this S2 coil. Now you can see due to the current flowing through this S1 coil, only magnetic field is only existing inside this S1 coil also. Okay, only inside the S1 coil magnetic field is existing. Okay, outside this S1 coil magnetic field is very weak and can be neglected. Okay, so magnetic field in this case is only existing inside this S1 coil. Okay, so the flux linked with this S2 coil. Now we are not going to take the whole area. We are not going to take the whole area of cross section of this S2 coil in the flux linkage, because magnetic field is not existing throughout the whole area of cross section. Only magnetic field is existing inside the S1 coil. Okay, so flux linkage with solenoid S2 will be N2 phi 2 will be equal to N2 B1, that is the magnetic field produced by S1 coil, into. Now why we have not written A2 here? Because magnetic field is only existing in the A1 area, that is inside the S1 coil. So A1 is written here. So N2 pi R1 square. Okay, so area is same in both cases. So area of cross section is same in both cases. Okay, so N2 pi R1 square mu naught N1 I1. Okay, so N2 will be small n2 into L. Okay, so pi R1 square mu naught N1 I1. Now clubbing all the things, so N2 phi 2 will be equal to mu naught N1 N2 pi R1 square L I1. Okay, so substituting N2 phi 2 equal to M21 I2 from equation 6.10. Okay, so 6.10 equation was N2 phi 2 equal to M21 I2. Now compare this equation with the equation we have calculated. So after comparing M21 I1 will be equal to mu naught N1 N2 pi R1 square L I1. Okay, so I1 is common here, so M21 will be mu naught N1 N2 pi R1 square L. Okay, now you have seen that M12 is also results in same thing, mu naught N1 N2 pi R1 square L, and M2 1 representing the same equation, mu naught N1 N2 pi R1 square into L. Okay, that means M12 equal to M21, 6.11 equation. So comparing the two expressions, we get M21 equal to M12, which is equal to M. Okay, so M21 equal to M12, we are representing both the terms with M, generalized term, which is equal to mu naught N1 N2 pi R1 square L. Mark it as 6.12 equation. So does mutual inductance of two coaxial solenoid is independent of which coil carries the current? Okay, we have discussed both the cases. In first case, S2 was carrying current, and in second case, S1 was carrying current. Okay, so mutual inductance is independent of which coil carries the current. Okay, so mutual inductance will remain same, either S1 is carrying current or either S2 is carrying current. Okay, so mutual inductance of two coaxial solenoid will be M equal to mu naught N1 N2 pi R1 square L. So mutual inductance depends only on the geometry, that is N1, N2, R1 and L. Okay, so mutual inductance only depends on the geometry of the coils, that is N1, number of turns per unit length of first coil, N2, number of turns per unit length of second coil, R1, that is the radius of the smaller coil. Okay, and into, and other thing is length of the both coils, and medium within the solenoids. Okay, if a medium with relative permeability mu r, okay, if we are inserting some another material mu r is present inside the solenoids, then so M will be equal to, if there is a medium that we are going to insert inside the solenoids, then mutual inductance will be mu naught mu r. So mu r will be multiplied additionally. So mu naught mu r N1 N2 pi R1 square L. Same length ensures uniform field distribution and complete flux linkage. Okay, so if we are taking same length of both the coils or solenoids, okay, so it ensures that uniform field distribution along another coil, okay, and complete flux linkage. So relation between induced EMF and mutual inductance. Consider two coils C1 and C2 placed nearby having n number of turns N1 and N2. EMF is induced in coil C1 wherever current through coil C2 changes. Okay, so current is flowing through C2 coil and it is being changed. So EMF is induced in coil C1. So let phi 1 be the flux through coil C1 when current in coil C2 is I2. Flux linkage with the C1. So what is the flux linkage with C1? That is N1 phi 1, which is equal to M. M is the mutual inductance into current flowing through the C2 coil, that is I2. Mark it as this was 6.7 equation. Okay, so where M is the mutual inductance of two coils. So differentiating N1 phi 1 equal to Mi2 with respect to time, then it will result in d N1 phi 1 upon dt equal to dmi2 upon dt. So induced EMF in the coil, in the C1 coil, will be epsilon 1. We know that formula according to Faraday's Lenz's law, induced EMF will be equal to rate of change of flux through the coil. Okay, so now there are two coils. Current is flowing through the second coil and EMF is induced in the first coil. So in EMF induced in the coil C1 will be equal to flux change of flux in the first coil. So that is equal to N1 phi 1. So epsilon 1, that is EMF in the coil C1, will be equal to minus D, and the flux linkage with the first coil is N1 phi 1 upon dt. Okay, so we know that N1 phi 1 is equal to Mi2. So put Mi2 in place of N1 phi 1. So epsilon 1 will be equal to minus D Mi2 upon dt. M is constant, mutual inductance is constant. It will come out of derivative. So epsilon 1 will be equal to minus M di2 upon dt. Okay, so EMF induced in the first coil is equal to product of mutual inductance and rate of change of current flowing through the second coil. Okay, so if we are changing the current through the second coil, then EMF will be induced in the first coil according to this formula. Okay, if we are not changing the current, then di2 by dt will be 0. So EMF induced in the first coil will also be 0. So there should be a change in current in the second coil to induce the EMF in first coil. And negative sign represents the polarity of the EMF. Okay. So there is example 6.8. Two concentric circular coils, one of small radius R1. So there it is a special case of mutual inductance also. We have discussed mutual inductance with two solenoids or coils having n number of turns. Now coils having one turn. Both coils have one turn. Single turn coils. Okay, so two concentric circular coils, one of small radius R1 and other of large radius R2, such that R1 is much smaller than R2, are placed coaxially with centers coinciding, obtain the mutual inductance of the arrangement. Why we are taking R1 much less than R2? So that the flux linked with the R1 or magnetic field through R1 will be uniform. Okay, so if we are taking R1 comparable to R2, then the field, that is field lines that are passing through R1 will not be uniform. Okay, so it will make to calculate the flux through R1, flux through the first coil having radius R1 complex. Okay, so to remove the complexity, we have taken R1 much less than R2, so that field lines that are passing through R1 will be uniform, and we can calculate the magnetic flux through R1 easily. Okay, let's see the solution. So I2 current is flowing through the large coil having radius R2. Okay, so if I am speaking R2, then I am pointing to larger coil. If I am speaking R1 coil, I am pointing to inner coil, that is smaller. So magnetic field at the center of the coil with radius R carrying current I is given by. So we know that magnetic field inside the coil at the center of the coil is given by having radius R and carrying current I. So magnetic field at the center of the coil with radius R carrying current I is given by B equal to mu naught I upon 2R. That relation we have discussed in moving charges and magnetism. So let outer coil with radius R2 carry current I2. Okay, it is shown in the figure also that outer coil is carrying current I2 having radius R2. So field at the center of the outer coil is given by B2 is equal to mu naught I2 upon 2R2. Okay, one reason also, magnetic field at the center of the current carrying circular coil is uniform. Okay, another other regions beside center magnetic field is not uniform. Okay, so the other regions at the center magnetic field is uniform, but at any other place other than center, magnetic field inside this circular coil will not be uniform. That's why we are taking this R1 much less than R2, so that it will be near the center. Its area of cross section will be near the center. Okay, so that's why magnetic field through this R1 coil will be uniform. because its radius is very, very small, and magnetic field near the center is uniform. So field at the center of the outer coil is B2 equal to mu naught I2 upon 2R2. I2 is current flowing through the R2 coil, and R2 is the radius of this larger coil. Okay, so magnetic flux phi1 through the small coil. Now we are going to calculate the magnetic flux through the inner coil, inner smaller coil. Through the small coil, due to magnetic field B2 is given by phi1 equal to B2 A1. So B2 is the magnetic field produced by the larger outer coil at near the center, and A1 is the area of the inner coil, that is smaller coil having radius R1. So A1 is the area of the small coil, and A1 is equal to pi R1 square. So magnetic flux through small coil phi1 equal to pi R1 square B2. Okay, so substituting the value of B2 we get, so we have calculated the B2 in the previous slide. So phi1 equal to pi R1 square, and what was the B2? B2 was mu naught I2 upon 2R2, because current is only flowing through outer coil, and magnetic field near the center of the outer coil is given by mu naught I2 upon 2R2. And this R1 coil is very, very small as compared to the outer coil. So its area of cross section is lying near the center. So magnetic field through this inner coil is nearly uniform. So it will be equal to mu naught pi R1 square upon 2R2 into I2. Okay, which is equal to M12 I2. Okay, we know that flux linked with the coil is given by M12 I2. Flux linked with the inner coil will be equal to mutual inductance of first coil with respect to second coil into current flowing through the second coil I2. Okay, so comparing both these equations, so mu naught pi R1 square upon 2R2 I2 equal to M12 I2. So I2 is common. So M12 is, so magnetic flux through small coil phi1 equal to M12 I2, where M12 is the mutual inductance of small coil with respect to the large coil. So equating flux through small coil, then M12 I2 will be equal to mu naught pi R1 square upon 2R2 into I2. So M12 equal to mu naught pi R1 square upon 2R2. So which is different from the case of solenoids. Okay, in solenoid M12 was different. But this is a special case when there is only one turn, single turn coils. Okay, and this R1 is much greater than R2, means radius of inner coil will be very small as compared to the outer coil. So then mutual inductance of first coil with respect to second coil will be equal to mu naught pi R1 square upon 2R2. Okay, so this is different case. So M12 equal to mu naught pi R1 square upon 2R2. Mutual inductance of small coil with respect to the large coil, and M12 is equal to mutual inductance of large coil with respect to small coil. M2 will be equal to M. Okay, so this M12 is this, M21 is the mutual inductance of large coil with respect to small coil, which is equal to M, because both will be same. Okay, as we have discussed in solenoid case, then M12 and M21 is same. Similarly, in this case also M12 and M21 will be same, which is denoted as M only, generalized term. So does mutual inductance of two concentric circular coils, M will be equal to mu naught pi R1 square upon 2R2. Note that we calculated M12 from an approximate value of phi1, assuming the magnetic field B2 be uniform over the area pi R1 square. However, we can accept this value because R1 is much less than R2. That thing I have already explained, that magnetic field near the center is uniform. That's why we have taken R1 much less than R2. And that's why we have approximate the value of phi1. Okay, if R1 is R1 coil is comparable to R2 coil. Okay, it is its size is comparable to outer coil. Okay, then magnetic field through it will not be uniform. So phi 1 calculation of phi 1 will not be accurate. Okay. So summary, the basic concepts we have discussed. Flux linkage is N phi. Basic inductance definition is L equal to N phi upon I, which is N phi is proportional to current and N phi is equal to Li. So L will be N phi upon I. Unit of this inductance is Henry, which is denoted by H, and it can be represented by Weber per ampere. Okay. So mutual inductance. Mutual inductance formula for coaxial solenoid M equal to mu naught N1 N2 pi R1 square into L. Symmetric property M12 equal to M21 equal to M. Okay, so we have seen by derivation also that M12 mutual inductance of first coil with respect to second coil is equal to mutual inductance of second coil with respect to first coil, and which can be represented by as M, generalized term, because both are equal. We have proved it and verified in the derivation also. With relative permeability, if there is a material inserted inside the core of the solenoids, then M will be equal to mu naught mu R N1 N2 pi R1 square L. Induced DMF in the first coil due to the current change in the second coil. That thing we have also derived. So epsilon 1 will be equal to minus M di2 by dt. So rate of change of current in the second coil is responsible for the induction of EMF in the first coil. So formula expression for induced EMF is in that case. So general form of mutual inductance M is equal to N phi 12 upon I1 equal to N phi 21 upon I2. Okay, this is the general term. That in second bullet point, it is also represented that L is equal to N phi upon M1. So M will be equal to, for M12 it is N phi 12 upon I1. For M21 it is N phi 21 upon I2. Okay, so there are some practice questions you have to do yourself. What is the flux linkage? How is it related to inductance? What is mutual inductance? Induction. What factors affect the mutual inductance of two coaxial solenoids? How does the presence of magnetic medium affect the mutual inductance? In the derivation of mutual inductance for coaxial solenoid, why do we consider the same length for both the solenoids? Two coils have a mutual inductance of 0.2 Henry. The current in the first coil changes from 2 ampere to 0 ampere in 0.1 seconds. Calculate the magnitude of induced EMF in the second coil. Okay, so this is all about today's lecture. We have to do the DPP. Okay, first question. Mutual inductance M12 of solenoid S1 with respect to solenoid S2 is given by. You can write your answers in comment section. Which option is correct? Mu naught N1 N2 pi R2 square L, mu naught N1 N2 pi R1 square L, mu naught N1 N2 pi R1 R2 L, mu naught N1 N2 pi R1 square upon L. Which option is correct? Yes, second. The self-inductance L of a long solenoid with cross-section area A, length L and N turns per unit length is. Okay, self-inductance is not there in today's lecture. Okay, it is question of tomorrow's lecture. Okay, so I am marking randomly here. The energy stored in an inductor with self-inductance L carrying current I. This is also tomorrow's lecture. Okay, for two concentric circular coils, radii R1 much less than R2, the mutual inductance M is proportional to R1 square upon R2, R1 R2, R2 square upon R1 or R1 square upon R2. Which option is correct? First, yes. The magnetic energy per unit volume solenoid is, this is not today's. Okay. Okay, this is tomorrow's. So I marked randomly. Okay. Okay, I hope you enjoyed the session. Thank you.